Thank you. Hi everyone, so I'm Pierre-Marie and this is Raphael. We are both software engineers at Adacor, and today we'll talk to you about Langkit, which is about to bring source code analysis to the masses. So Langkit is a meta compiler. Okay, what? Langkit, in this project, we created a DSL to make it easy to basically implement front-ends like compiler front-ends. So Langkit generates libraries which can be used to be the first half of compilers that can also be used in debuggers to parse an expression and to evaluate it. For interactive code browsers, when you can click on an identifier and that leads you to the definition of this identifier. To write also static analyzers like linters, or think of Semantic ID or this kind of thing. And also we want to make it easy to write refactoring tools that, for instance, you ask on your whole code base, okay, please rename this type definition and all the usage of it. So we created this originally because when in the Ada ecosystem we exactly need this kind of library to improve tooling in general. So Langkit was for that, but it can be used for other languages as well. So let's have a brief tour on the DSL and how you express things, how we can use Langkit actually. So first of all, so for now, the Langkit, it's a compiler. You feed it a Python-based DSL. So you're not really writing Python, it's just using the Python syntax to express something else. One day we'll probably have a dedicated syntax. So first of all, that should look familiar. When you create a language, the first step is to create a lexer for it. So you can split a string into a sequence of tokens. So the first thing to do is to actually define the list of tokens that your lexer is supposed to create. And then you provide rules that, well, start from regex and compile into some automata to actually implement the lexer. So this should be familiar if you have already written a specification for flex, for instance. It's the same mechanism. The next layer is to actually define the list of three nodes that your parsers are going to create. So here you can see, well, using the Python syntax, you define a class hierarchy where a node can be extracted and so on. And each node can have a list of fields. So for instance, if you have a function definition, you have a field that gives the name of the function, the list of arguments, the body of it, etc. So you defined the tree. And the next step, you write passing rules. So like in Bison, if you know it, or GAC, you write parsers in a recursive descent fashion to, well, say, okay, this rule, if you find this token and this token, you will produce this node, and this in a recursive fashion. So, and this is compiled into a parsing library that is based on packrats. So Langkit will take all the definitions I showed and will compile that. In particular, it will analyze the grammar, and from it will say, okay, we're creating this kind of node with this kind of field and this kind of field, so it will perform type inference. And if you remember here, so I can define fields without providing them type. Well, the grammar will infer type if they are not specified. Otherwise, you can specify them to be more explicit, and Langkit will check for consistency. Okay, so now we have, well, the bottom layer of your front end. So you have lexing, parsing, and the next step is semantic analysis. So the first thing, so semantic analysis is the part that will answer questions such as, okay, what is this identifier referring to? What is the type of this expression, and so on. So the basis for that is what's called in literature scoping or lexical environments. So here we provide, in AST nodes, we provide special annotations that will describe, okay, we have a function. Okay, this function creates a scope, and everything that will happen inside it will act on this scope, again in a recursive fashion. And so these special annotations will enable you to create mappings, so kind of dictionaries that map from identifiers to nodes. So this is the first step. And then you will implement semantic analysis using, well, you add yet another kind of annotation on nodes. So this kind of annotation, so it's methods, we call them properties in Langkit. The public one will actually implement the semantic analysis API that you want to provide to your users as a library author, such as here. So we have a var_decl property that will, well, on a variable reference, it will fetch the corresponding variable declaration. And you can also have private properties that will just be implementation details, and users won't see that. And so these properties, you write them using functional programming language that we created. So this is this part here. So here you take, for instance, the current node that is a variable reference. You take the environment that is associated to it, and you perform a request giving its name. So it's supposed to, if the variable definition is not the scope, it will return it. So here we don't see it, but there are types in this. It's a functional language that is typed, and with type inference. So Langkit, when it compiles it, make sure that your expressions actually have are meaningful, and will reject incorrect ones. Okay, so with just this base, we can already do parsing analysis for a great deal of languages, and this is cool. So all you have to do is to write all the properties you need to answer the request that you want users to have access to. But there is still a missing piece, which is in ADA we needed it, which is overload resolution, which is n-type inference. These are problems that are difficult to solve just using a mere functional language because, for example, here, let's see, we have an example. Well, we have several functions that have names that are equal, but they accept arguments and have return types that are not exactly similar. So for simple cases, such as this one or this one, well, here we have a call to F1, so one of these two, that takes an int, so an integer literal, so it has to be a call to the first one. So here we have a floating point number, so it has to be this one. Here we call F2 with an integer literal, and there are no F2 function accepting integer literals, so this results to nowhere. And you have complex cases such as this one. So we can see here that we may be able to solve with some fancy algorithm which F2 is called here. You see, it takes a character literal, but okay, both F2 takes a character literal. So here the difficult thing is that solving actually doing the resolution of names is a problem that requires some non-local knowledge. Resolving which function is called by this F1 call can depend on something that is quite far. So yeah, it requires non-local knowledge.
So just to add something about that, this problem is ADA specific. In ADA we have that, so you can overload on the return type of a function. But in, for example, functional programming languages such as OCaml, you have a non-local type inference, and you have the same kinds of problem. So what we are trying to do is have a general solution for these kinds of problem.
And this general solution is, well, so if we take the example that I just quoted earlier, so this is the complex call that we want to solve, we can collect a set of constraints. So here, so let's, for the purpose of discussion, let's call this function call C, this function call B, and this one A. So we see that A takes character arguments. So here we have this constraint. So A, its first argument, well, its type must be a character. We pass the result of A as an argument of B. So the return type of A must be the type of the first argument of B. The same applies for the outer call. And because we're calling, because A is about calling F2, well, we see that A is one of these two. Yeah, they are on the same line. One of these two declarations. Same goes for B and C. And so you collect a set of constraints, and then, well, in Langkit, we provide, along with the functional language, a satisfiable, what's the name?
A solver.
Yeah, a solver.
Please don't say satisfiability.
Yeah, blah, 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 blah. So something that takes a set of constraints and that give you, hopefully, the unique solution to this problem. And so using all these building blocks, well, you're supposed to already be able to express semantic analysis for quite a large corpus of languages. And I will leave Raphael speak about what's next. Here. Let's be quick, we don't have much time.
Thank you. Okay, so Pierre-Marie described to you the mechanism by which you describe your language, so the language specification. And this is what you as, like if you want to write a new language frontend, this is what you will do. But then you will have users for your library, people who want to, for example, write refactorings for Ada or whatever language. For the moment, we only have Ada, so Ada or Ada. But then we expect to have a lot more. So I'm going to talk about what we generate. So if it's not obvious yet, because it's a bit complicated, the meta compiler is not a very simple project. This is the pipeline of Langkit. So basically, you will provide your language specification. This is what Pierre-Marie has been talking about so far. And then you feed that to Langkit, and it will generate a library, like something you can call from your code, and that will provide you knowledge. So this library is in Ada, a language that you maybe never heard about. But fear not, because we provide a lot of bindings to other languages, like C, Python, and it's really easy to generate bindings for other languages. And on top of that, the hope of the whole project is to be able, from this language specification, to generate generic tools that I'm going to get into. So the base library is made in Ada. So it was an easy choice for us. I'm just going to point at the name of the company so that you understand, Ada Core. Basically, we needed a low-level language that can produce fast codes and that doesn't have memory management policy built in that would be complicated for us to handle in IDEs. For example, we didn't want to ship a GC along with the libraries because if you need to have results fast, maybe it's not a very good idea, etc., etc. But we could have chosen another language, but Ada was an obvious choice for us because we have a lot of Ada knowledge and it's right on target for this use. So since not a lot of people use Ada, we provide bindings to C and to Python. And Python is the de facto scripting language of the ecosystem. So once you generated your library, you can right away use it from Python, launching an interactive shell, and for example, parsing a source code and asking for knowledge about the code. And it's easy to generate bindings to new languages because Langkit has the knowledge from the language specification about everything, the data types, the fields, the functions that are available, so it can very easily generate bindings to other languages. So, interesting point about Langkit generated libraries is that they are crafted for incremental analysis. The reason we express, for example, the properties in a functional language, and the reason everything is declarative, is so that we have freedom in the implementation to do something that takes this semantic and generate an incremental analyzer for it. So as little state as possible in the spec so that we can do an incremental analyzer. And for Ada, what this means is that if you change a file, you don't need to recompute every file that depends on it every time like most compiler would do. I know some compilers are more clever than that, but GNAT is not, for example, which is the main compiler for Ada. So this was very important for integration into IDEs for us. So this is an example of something we did with libadalang, which is an engine generated with Langkit. And it's a static analyzer for Ada. It's very small. It's, this code is the whole static analyzer using the libadalang library. What it does is something very simple. It checks for binary operators like addition, subtraction, and checks if syntactically the two operands are the same. So it's a very simple static analysis check. And surprisingly, we run it on our code bases, and we found a lot of bugs in our code bases, despite extensive testing and other more powerful static analysis run on it. So once you have a you have a syntactic analyzer for your language, well, if you have that at your fingertips, you can do a lot of stuff that is really interesting. And this could be adapted for another Langkit frontend. We have a Python parser, for example, and we have this one running on Python too, so it's very easy to adapt because the API is exactly the same. So what we also generate automatically from your grammar definition and your tree definition is an unparser. So we have a mean to parse code, but we also have a mean to take a tree and produce a new source file from it, not using any source information. So this is useful because if you remember, Pierre-Marie told you that we want to be able to do refactorings with the libraries. So it means that you can modify the tree and then you can call an unparsed primitive and it will generate a new source. So this is a very neat abstraction to build refactorings upon. So it uses the grammar and the ASCII definition. You don't need to write anything else. It will generate the unparser automatically. And so you can use it to do this kind of stuff. So this is an ADA source code, okay? Simple hello world program, very simple. And then we want to change the string literal to byword, but not using sed or whatever, but using the tree directly. And so this is an example program that you can do using the ADA frontend. You will look for the call, and then you will start a diff and rewrite the string literal and put byword instead of hello world. So this is all done at a tree level, not at a source level. And then you apply the diff and you obtain the new program. So this is very convenient. I don't know how much time I have left. Very little, actually. So we ship a number of tools along with the libraries, and the hope from the Langkit project is that the more we go along, the more generic tools we have that you can use. So once you have a language specification, you have generic tools working on it. So we have simple command line tools that you can use. Playground is an interactive shell based on IPython. Parse is just an AST dumper. But we have more interesting stuff, like a prototype for a generic code indenter, for example. So this is for ADA, and what you would do is provide a declarative way of indenting your code for the tree. So you say, for a package declaration, for example, I want the public and the private part to be incremented by block rule, which says increment by 3 columns. And then the engine will do that automatically. And if you have a new language frontend, all you need to do is to write this map, and you have an indenter for your language. Syntax highlighter could be produced along the same way. We have all the information we need to produce a syntax highlighter. And going this way, we could imagine at some point being able to provide a whole server for the language server protocol. So you write your language specification, you write how to do go-to definition, auto-completion, etc. And it will generate the engine that does it, and you can directly plug it into your editor. So for the moment, this is not done at all. It's just a dream. But we have a prototype for it, which is just an EOVim plugin, and that already does quite a lot of stuff like indentation, go-to definition for ADA, and it does a subset of that for Python too, because we have a Python frontend. So we already have a few prototypes for frontends based on Langkit. So we have ADA, libAdaLang, that is the most complete. And we have a Python. So for Python, we mostly have the parser. But we have a very simple model of how the scoping works. So in Python, since it's a dynamic language, you don't really have static scoping. But you can model it so that you can use it in IDEs. So we have that. And we played with other simple languages like JSON or kconfig to prove that we can actually generate frontends for more languages. And for the moment, that's all. But we hope that raising awareness about the project, people will try to write new frontends, maybe. And tell us that it doesn't work at all and that we need to fix everything. So thank you for listening. You can find the sources for Langkit on GitHub here. And we have a tutorial, so if you want to write a new front-end for Langkit, we already have a tutorial that you can find here. So it's still a work in progress. APIs are moving, and for the moment, except the tutorial, we don't have much more doc. But we will gladly accept any feedback, issues, pull requests, etc. Thank you very much. Questions? Yes, go ahead.
Do you plan on, for example, creating a code generation DSL so somebody can maybe use it to prototype a simple backend for his language or something like this?
So the question was, do you have plans to be able to generate a simple backend for the languages? I imagine you mean declaratively also?
Yeah.
Yeah, of course. So of course you can write a backend using the front end for the moment, but that's not what you're talking about. We had some ideas about that. It's really not our target at work, but nothing prevents it to do it if you like. It's a very interesting topic. So yeah, I have a few ideas of how to do that, but nothing in the works for the moment.
Maybe we'll do that once in our spare time, but maybe.
Yeah. Yes?
Does your tool preserve comments?
Yes. So we have a concept called trivias. And so when you parse the tokens, you can say, this is a token relevant for the tree, and this is a token that you need to store in the tree, but that won't imply,
Interfere with parsing.
Yes, thank you very much.
Interfere with parsing.
So in that case, it will be stored in the node. What we don't do for the moment is provide a rewriting API that allows you to insert comments, but we plan to add that at some point too. I think there was a question.
It was that question. So.
Okay, cool. Yes?
What's the expressiveness of your constraints?
So the question was, what is the expressiveness of your constraints? Since despite the appearances, I'm not very advanced at constraint solvers, could you precise your question a little bit?
For instance, you said that you can implement type inference like in ML.
Mm-hmm.
I think you need to be able to convey the typing environment inside the constraints. I'm not sure that you can.
For
example.
Yeah. So what the precision was, if you want to type ML with it, you need to convey the type environment in the constraints. So we have some ways of doing that. I don't know yet if they are going to be sufficient for ML. I'm working on a prototype, and at some point I would like to publish a small example / paper about that. For the moment, we really crafted it for Ada, and then we are going to extend the semantics so that it is useful for more than that. Okay, thank you very much.